The world's biggest chip maker is building chips at the atom scale. 2 nanometers, just 10 silicon atoms wide. This is the biggest architecture shift in 14 years.
To grasp how small 2 nanometers really is, consider this. A human hair is 80,000 nanometers wide. A red blood cell, 7,000. A single strand of DNA, just 2.5. We are engineering at the boundary of physics itself.
But here is the myth we need to bust. 2 nanometers is not the actual transistor size. It is a marketing node name. What matters is the architecture underneath. And that is where the real revolution lives.
Let us trace the journey. 250 nanometer planar transistors. Back in the 1990s, then 65 nano, then 28. Down to 7, each generation pushed physics further. But at 5 nanometers, the old FinFET design hit a wall.
FinFET wraps the gate around 3 sides of the channel, like a fin. It dominated for over a decade. But below 5 nanometers, current leaks from the exposed bottom. Power efficiency collapses. A new approach was needed.
Enter gate, all around nanosheets. The gate now wraps the channel on all 4 sides. 0 exposed surface. Complete electrostatic control. This dramatically reduces subthreshold leakage, and it unlocks the next decade of scaling.
The performance gains are significant. 15% faster at the same power, 30% less power at the same speed, and 20% denser transistor packing. A generational leap over N3E.
None of this works without extreme ultraviolet lithography. A carbon dioxide laser vaporizes tin droplets. This creates 13.5 nanometer light. 11 mirrors focus it onto the wafer. Only ASML can build these machines.
Inside the fab, over 1,500 process steps unfold across 3 months. Design, photomask creation, EUV lithography, plasma etching, atomic layer deposition, and final testing, all in a class. 1 clean room, costing over $20 billion.
Let us compare the specs, head-to-head. N2 versus N3E. Transistor density jumps by 20%, packing more switches into every square millimeter. Performance gains of 10 to 15%, power reduction of 25 to 30%, and the shift from FinFET to GAA architecture.
The first customers are already locked in. Apple for the A20 and M6 chips arriving in 2026, AMD Zen 6 on the 2 nanometer node, and PDAPAC's next Dimensity flagship, all arriving in 2026.
If you're finding this valuable, hit subscribe. The best part is coming next.
The Foundry Race is intensifying. The top foundry leads with N2 at roughly 70% yield. Intel 18A follows, shipping GAA plus backside power together. Samsung SF2 trails with yield still around 55%, but Intel's backside power delivery gives it a unique advantage.
Speaking of backside power, traditional chips route power and signals on the same side, causing congestion. BSPDN moves power delivery to the back of the chip. The result? 10% smaller die area, lower voltage drop, and 2 to 6% frequency boost.
Let us talk stocks. The foundry leader at 2 trillion market cap, the chip maker itself. ASML at 680 billion, the only EUV machine maker. Applied Materials and Lam Research for deposition and etch. KLA for inspection. Tokyo Electron for coating systems. These companies form the entire supply chain.
The AI impact is transformative. 2 nanometer chips slash training power by up to 30%. Real-time on-device inference becomes standard, and data center electricity costs drop dramatically. The AI chip market is projected to exceed $300 billion by 2030.
Looking ahead, the roadmap is ambitious. N2 arrives in 2025, then N2P with 5% more speed. A 16 brings backside power in 2026. A 14 arrives in 2028. And CFET, stacking transistors vertically, targets 2030 and beyond.
From GAA nanosheets to EUV lithography to backside power delivery, the semiconductor industry is rewriting physics, and it is just getting started. Like and subscribe for our next deep dive. Intel 18A versus the leading A16 node.